Welcome to the first of our new kind online lectures. I hope first of all that you're all doing well, and I would like to tell you that if you have any concern about courses or also more serious about health and yourself, please let us know and we'll try to help if need be. Okay, now as a start, I would like just to summarize what we have done last time with a very short overview of the last lecture. So last time we went through the angular momentum, so this is just a quick summary of what we went through. So we will start with angular momentum operators that we have defined in the previous lecture. So as you can see, the angular momentum, as you can see from the picture, is a vector, which is the vector product between the position vector and the momentum vector. First of all, I want to say that this is the first time I'm doing something like that, so things might not go as smoothly as one would like to, so I apologize in the beginning. Okay, so this is just the position vector and then the momentum vector. So the angular momentum is the vector product between those two. And as you see, we're only using angular quantities. So we have the angular momentum, we have the moment of inertia, which is basically the equivalent of the mass, which is the mass times the radius of the rotation squared. And then we have the angular velocity, which is omega, and is written here, which is the variation of the angle with respect to time. Then if you want to see how this vector product operation works, then you have to look at the components which are down here. And so each component of the angular momentum is related to the momentum and position the following way. So we went through a quick way of remembering this formula. So remember that if you're looking at Lx, it means you have quantities in y and z, and then you have y and pz with the plus sign because you're doing in the, let's say, clockwise direction. So you have Lx, y, and z. If you instead have the opposite permutation here, x, z, y, then you need a minus sign. So, and then in this way you can find out what the different components are. Of course, when you go to quantum mechanics, you always have to recall what the different operations are. And for instance, the position operators are just multiplication by the position itself, whereas momenta become derivatives. So we have minus IH, so just to remember, I'll just write it down here. So P x is minus IH derivative with respect to x. So if you substitute this for px, py, and pz in the expressions, you end up with this following expression where you have derivative with respect to z and derivative with respect to y in the first, and so on. And then minus IH is a multiplicative constant and we can take out. Okay, this is just for definition. Then we went through I apologize, this is the first time I'm using this thing, so it's gonna take some time. So we went through a very quick way of remembering how things are, and the quick way is like to make a parallel with linear motion, where we have the mass, we have the moment of inertia, wherever we have the position, we end up with the angle, and then all the others just follow simply by substituting those. So the velocity, for instance, is a variation of the position with respect to time, and then it becomes a variation of the angle with respect to time, and so on. So the momentum is mass times velocity. It means it becomes the moment of inertia times the angular velocity, and so on. Kinetic energy, p squared divided by 2m. Kinetic energy, L squared divided by 2I. Okay, so this is just a quick way of remembering it, and so you only have to remember mass becomes moment of inertia, position becomes angle, and everything else will just follow by what you know from the linear motion. Only problem here is that things become a bit more complicated when we go to 3D, and we will see it later on. Okay, now let's go on. So then we open a parenthesis here when it comes to the transformational coordinates. In particular, what I would like you, so I will not go through the whole derivation as I did last time. What I would like to you to focus your attention is on this last set of formulas here. Okay, why? Because this is going to turn very useful when we will look at the angular momentum wave functions in 3D, because this will help us define the different functions, and will help us see what is the relationship between the orbitals you're used to think in terms of, like px, py, and pz, the x squared, the y squared, and so on, and these coordinate definitions here. So please remember what x, y, and z are in 3D as function of the radius, as function of the angle phi, and as function of the angle theta. So r appears in all of them, as you can see. Z is the easy one because only has a reference to the cosine of theta, so which means that then both x and y will have sine of theta, and then x will have cosine of phi, and y will have the sine of phi. Okay, so now we go on, and we will go to the final one, which is the definition of the problem, which is the particle on the ring. Okay, so the energy for a linear motion, I'll write it again here. The energy, when we looked at the particle in the box, the energy is p squared divided by 2m, which means that for us it becomes L squared divided by 2I. So then we only have one direction because we have rotation only in the xy plane, which means that we will only have Lz to look at. Okay, that's the R only. It's like, basically it's like a particle in one-dimensional box. The difference is that now our variable is no longer the position, so the length of the box, the particle bouncing back and forth from one side to the other of the box, but now it's just the particle rotating, and our variable becomes the angle. Okay, so it's still a one-dimensional problem. Okay, although the particle is moving in 2D because it's moving on a circle, but we just make it transformational coordinate, just we look at the angle. That's the only important one. So Lz looks like that. So is now, again, as P is Z is minus IH derivative with respect to Z, then Lz is minus IH derivative with respect to phi. Okay? And then we can write the Hamiltonian as, we write it as p squared divided by 2m. Here we write it as L squared divided by 2I. And then we work out the eigenfunction. Again, I will not go through the derivation because we've done it last time. Please look it up in the book. But the wave function then looks like this, is e to the I ml phi. Okay? So notice that now we have the imaginary constant I, we have a quantum number that can have positive or negative value, so ml will be plus or minus 1, plus or minus 2, plus or minus 3. Okay? And then we have the variable phi. What I would like you to think about, and these are questions left for you, is what is the normalization of this wave function? So how do we normalize the wave function? How do we make sure that the square of the wave function when it's integrated is 1, What are the boundary conditions? And the boundary conditions, we have looked at them. We have looked at, we need those boundary conditions that will guarantee that when we make a full circle, we make a full round around, the particle makes a full round, then the wave function value will be exactly the same. And this is guaranteed by this form. And then the last two questions are, which direction is the particle going? So which is the direction of the rotation, and do we have nodes? So does this wave function have nodes? Let's say places or points where the wave function is 0. So this is an important question in general, so to find the nodes of the particle. Okay, this was just a summary of this part. Please think about the questions, and then I'll see you for the next lecture.